Hello friends. So, we have discussed the basic idea behind solution of simultaneous equations, what is involved, how is it organized, that is conversion transformation of the system of equations into an equivalent system of equations which has identical solution as the original, but it is easier to solve. So, the first exposure to direct solvers that we had in our school was elimination of variables, and technically that is referred to as Gaussian elimination. So, we go back to our school days, and I call this as the school book approach, how we did while we were at school, the Gaussian elimination. So, essentially it involves successive elimination of variables by elementary row operations, that is linear combination of rows is does not change the solution, multiplication of a row by a constant does not change change the solution, and so on. I mean so interchange of rows is not an issue, and row multiplication by a constant by where k is a non-zero constant. So, that is also acceptable. All these operations, they do not cause any change in the solution. Row addition, I mean 2 rows can be added and replacing another row, that is also possible. So, that is also not going to change the solution. So, let us take the same system of equations that we had originally. So, 2, 1.5, 1.5, 2, this is a symmetric matrix by the way, and 2 variables x1, x2, let us call it x1, x2, and right hand side vector is 3 and 2. So, the idea is to reduce it to row echelon form by successive elimination. So, that will be leading diagonal term of the variable being eliminated is called the pivot. So, from this x1 is being eliminated from equation 2, right. So, when we look at the equation 2, it is the equation 2 only involves x2 and there is no x1, I mean the coefficient of x1 is 0. So, x1 is being eliminated. So, the equation that is x1 that is being eliminated. So, the diagonal term corresponding to x1 in the coefficient matrix, that is this particular element in the diagonal position. So, this is called pivot element, and pivot, that is important because that goes in the denominator, and that is why it is it has special significance. We will see why that is so important. So, what is done is row 2 is replaced by a scaled version, I mean adding a scaled version of row 1 with row 2, and that resultant is what is replaces row 2. So, when we do this, then essentially we scale it down by this vector, this scalar pivot element, and multiply with whatever was the coefficient here, negative times of that, and then add equations, add the 2 equations. So, that would make x1 to vanish and resulting coefficients would change, I mean this coefficient of x2 changes and the right hand side vector also changes accordingly. And subsequently this system of equations can be solved, x2 can be solved as minus 0.25 divided by 0.875, and having computed x2, x1 can be solved from the first equation. So, back substitution gives us x2 is equal to minus 0.2857. I am retaining 4 significant digits here, and x1 is obtained by substituting this value of x2 in the first equation, and x1 is obtained as 1.714. So, what is wrong with this? This seems to have worked very well, and these are the standard procedure. I mean theoretically we can derive that equations, the solution of equations does not change under elementary row operation, and once we have this row echelon form, the equations can be solved by using back substitution, and that is a fairly straightforward procedure. So, what is wrong here? Wrong is in the sense, what if this pivot element A11 is very small in comparison to A21? That will increase the amplitude greatly. And if you recall our floating point representation, it is a logarithmic space. So, a large amplitude number incurs larger round of error, and that is the whole crux of the problem here in computation implementation, digital computer implementation of this Gaussian elimination. So, if the system of equations was so arranged that A11, the pivot element is for the variable that is being eliminated, is very small compared to the other coefficients, then the chances are that this elimination process will incur a very high round of error, and that will propagate through the solution, because once an error is introduced, that error is carried through the entire process, because if I incur an error in computation of x2, that erroneous value of x2 will also affect the computation of x1 here. So, not only there is an error in x2, there is an error in computation of x1 as well, as a result of the entire algorithm being structured as a successive elimination process, and that is a problem, and this is what we call as error propagation. Let us look at this. So, process uses coefficients computed in previous row operations, and round of errors are carried through and accumulated, because one row that is modified is used for subsequent operations, subsequent elimination of variables in subsequent operations. So, one round of error leads to another round of error and so on, and there will be several round of errors piling on top of each other. So, just to explain that problem of small pivot, let us look at this solution. Admittedly, these numbers are cooked just to drive home the point that even for I mean 2 by 2, such a simple 2 by 2 system, how horribly can things go wrong. So, again I retain 3 significant digits here. So, 0.00, just to make numbers within reasonable width, so that it fits in the slide. So, 0.001, 10, 1, 1, x 1, x 2, and the right hand side is 1, 2. So, again computing with elimination of the variable. So, R 2 replaced by linear combination of R 2 and R 1. So, applying Gaussian elimination. So, this is what it leads to, and 0 minus 9999 times x 2 is equal to minus 998, and if I reduce it to 3 significant digits, then I get it as a 1.0 10 raised to the power 4, right. And if I compute this solution, a backward substitution, then x 2 is evaluated as 0.1. If I divide it by this, so I will get 0.1, and when I substitute 0.1 here, the solution for x 1 evaluates to 0, because x 2 is 0.1. So, 10 times 0.1 is equal to 1. So, obviously, x 1 has to be 0. So, the solution that we compute is 0 and 0.1, whereas the correct solution is 1.9 some terms and 0.0998. So, 0.0998 is correctly represented approximately reasonably fine. 0.1 is a reasonably good approximation to 0.0998, but this solution, this round off value, round off result for x 2 leads to completely wrong answer related to x 1. And this is what is a problem with Gaussian elimination, naive Gaussian elimination, the school book approach that we have. And the entire thing is because of this small pivot element, because once it divides 1 by 0.001, this becomes too large a number compared to other numbers, and that leads to round of errors and subsequent blowing up of the calculation. So, how to guard against this? So, error propagation, I mean errors are going to be incurred. I mean once we have floating point operation, it is a given that every floating point operation will incur round of errors. So, how do I avoid incurring very large errors, or how do I prevent catastrophic propagation of this error such that the solution is still meaningful? All solutions are approximate. Any result, any number coming out of digital computer is an approximate solution. There is nothing like exact solution. Exact solution is a myth as far as digital computers are concerned. So, but the approximation can indeed be a very good approximation. So, how do we organize our procedures to get a reasonably good approximation, and that is the key is how do we contain the error propagation. So, what is the possible breakdown? So, possible reasons could be under constraint system coefficient matrix is not of full rank, then the solution is obviously impossible, but then near singular can also be have a problem. We have a problem because the equation that we had earlier, I mean the previous problem, that pivot element of 0.001, the system is near singular, and that is what is leading to problems, and that is what leads to excessive round of errors due to division by very small pivot. The result may be quite unusable. The small pivot in itself is not a problem, because if all the elements are of relative same order of magnitude, if the other term in the equation instead of being 10 had it been 0.002, that would not have been a problem. So, the smallness is a relative term. If the pivot is small compared to other coefficients in the equation, then that is a problem, because any scale, I mean any row can be scaled by a constant. So, small pivot is not really an issue on its own, but its smallness compared to other coefficients of the equation is a problem. So, how do we deal with this? So, this is one is scaled partial pivoting. What do we mean by that? So, the idea is it is not necessary, I mean to process the equations in the same order as they are presented. So, for example, what is listed as row 1 need not be treated as row 1. I could have handled row 1 as row 2 as row 1 and row 1 as row 2. If I did that, then you would realize that if I interchange the rows, the entire problem goes away, very simple. The pivot is not very small anymore, right. We will see how that works. So, not mandatory to process the equations in the same natural order as given. So, exchange rows to have the largest pivot scaled by the largest coefficient of the row for the variable being considered for elimination. So, we have whatever all rows are scaled by the largest coefficient. So, we have normalized equations, all equations are normalized to have largest coefficient being 1 in each row, and then we look at that particular row for considering pivot as which has the largest coefficient, and then we implement exchange of rows. So, that would eliminate the problem of using a very small pivot, which will lead to blowing up or amplification of round of errors. But this pivoting row exchanges destroys LU structure of Gaussian elimination. For example, if we store the multiplication, the whatever coefficients that we have for implementing that Gaussian elimination, for example, A21 by A11 minus of A21 by A11 in the position A21, because that coefficient would anyway be 0. So, we can store this coefficient, and then these off diagonal triangular structure and keep diagonal terms as 1. So, this becomes the lower factor, lower triangular L, and the other one is of course U. So, this becomes LU factorization of matrix A, and this is only possible when I do it in the once I decide the order and I process the entire system in the maintaining the same order, no further row exchanges anywhere. But if I do this row exchanges pivoting exercise, then it prevents it destroys this LU structure. So, that is one thing, one minor result that might be of interest. So, essentially what is done is it is again row interchange. I mean mathematically they can be implemented very easily, and there are row operations implemented as a scalar multiple, and permutations interchanges can be done by using permutation matrices if required for the analysis purposes, and then eventually they can be implemented as elementary row operations of matrix A. Same elementary row operations are performed on matrix B. So, ER is the modified identity matrix. So, we can interchange the identity matrix, interchange the rows, and that becomes the permutation that will once we multiply with this. So, it will permute exchange the rows, interchange the rows. And similarly, this ER is inverse is simply computed by substituting alpha instead of minus alpha in the jth ith position. So, row exchange can be implemented by permutation matrix, and that is just the interchange of the identity matrix. And this elementary row operation, that is done by using a scaled version of I mean linear combination of two rows. So, that is done by replacing the identity matrix coefficient J, jth ith position as minus alpha, and then multiplying that. So, this is how it can be implemented very easily on the it is very easy to develop a code on the basis of this permutation elementary row operation matrix and permutation matrix, and then the sequence of operations can be defined. So, the uh, the entire system, entire Gaussian elimination can be carried out as a series of matrix multiplication, elementary row operation matrix, permutation matrix, elementary row operation matrix, permutation matrix, and so on. The problem with this approach is there is a large scale movement of data in computer storage, and that data is stored in a slow speed storage area, and this will slow down the operation execution of the code, and that is what I refer to as steep performance penalty. So, what is essentially practical implementations are done is by making little bit of bookkeeping, keeping track. I mean, we do not interchange any data. So, the purpose of, we realize that the purpose of partial pivoting is merely to establish a preferred ordering of equations for sequential elimination of variables. So, as long as I develop a mechanism to identify which equation, which variable has to be eliminated from which equations in what order, then this interchange of rows etc., is not really required. It can be done in place, and that is what is done. I mean, by keeping track, by using an index array, integer index array, and that is it keeps track of which row is to be considered as a pivot row for elimination of which variable, and using that it can be the entire Gaussian elimination process can be computed, and this index array position can be used for back calculation or back substitution operation for calculation of the solution in the while computing the variables, solution for variables. So, this is all for Gaussian elimination. Then we have other approach, that is LU decomposition. Matrix A can be decomposed as a product of lower triangular and upper triangular matrix. Again, as I said, Gaussian elimination process itself is a, if I just use elementary row operations, that itself is a it will convert it into upper triangular matrix, and this entire process is a lower triangular matrix, and its inverse operation is easily computed by just changing the sign of that multiplier alpha. Instead of minus alpha, it will be plus alpha in the inverse of the matrix. Otherwise, E matrix are essentially identity matrix except for jth ith element. So, it is easy to see that matrix A is simply inverse of this. So, while we take the inverse, it will be order will be reversed. So, that is essentially L times U. So, that is the LU decomposition, and once we have this LU decomposition, these equations can be solved by two step process. So, when pivoting is performed, this factorization actually gets affected, because this will not be related to A after pivoting, but rather the permuted form of matrix A, PA. So, there are ways of handling that, but more I mean, this is theoretically it is possible that Gaussian elimination can also lead to LU factorization, but it is more prudent to use symmetric positive definite matrix can be decomposed using what we know as Cholesky decomposition algorithm, and in that case upper triangular matrix is going to be transpose of the lower triangular matrix. So, U is simply transpose of L, and matrix A is given as L transposed. And once we implement this lower triangular matrix and implement the product, we will find that we can actually work out one-to-one correspondence between the unknown equations, unknown terms of lower triangular matrix L and the coefficients of matrix A. So, L11 is computed as square root of A11, and then rest of the elements of first column can be computed by simply taking ratio of AI1 divided by L11, and similarly then subsequent column J, it can be similarly arranged by this standard algorithm. And once we have this the lower triangular entries for all the columns are available, and once we have this Cholesky factorization, then subsequently the solution of simultaneous equations can be computed by using two stage process, forward substitution and backward substitution, and then the solution, complete solution is known. Wherever Cholesky factorization is admissible, the system of equations is generally well conditioned, and no further pivoting is generally required. Of course, it is always a good practice to first estimate the condition number of the matrix, just to know whether the system of equations is well conditioned or not. So, that completes our discussion of direct solvers. You may explore this topic further and work out some of the, try to develop code based on the basis of this Cholesky decomposition and also Gaussian elimination algorithm that has been discussed, and try to implement the partial pivoting by using the index array. That would be a great learning exercise. In our next lecture, we start with iterative solvers, and that is a very powerful set of techniques and of immense application. Thank you.